So we have this pairing where we have some element of gamma naught n with this modular symbol, or just some matrix in SL2Z even, and this modular form, and this is going to be equal to this integral from alpha to gamma alpha of 2 pi I f of w dw, and this is independent of the choice of alpha, just some element in the upper half plane. And we want to exploit the duality of this pairing to study the spatial modular forms. And instead, we're going to study the homology of the modular curve x naught of n. So let's triangulate x naught of n, right? Because if we want to study the homology, the way you do that is you break it up into triangles. So starting with just the upper half plane. Okay, I'll just do it this way. So let's look at the following triangle. So this is a triangle. So it's a triangle between infinity, so I infinity, I'm just going to write infinity, the point 0 and the point 1. And these sorts of triangles are what we're going to use to triangulate. So we can think about this path. How's this set up? Sorry. There's a specific orientation that Cremona chooses in his book, Algorithms for Modular Elliptic Curves, and I want to make sure that I match that that orientation. So the idea is you're going to look at, so you can define for some element gamma, here gamma is actually going to be an element of SL2Z, or PSL2Z, not gamma naught of n, and we're going to find this to be gamma acting on 0 to gamma acting on infinity, right? The path between these 2 points. So this is as a path, and then i.e., not really a i.e., but really viewed as an element of, and now we have, normally we would have the real homology here, but we know that this is in fact going to be the rational homology by the Manet-Drinfeld theorem. So it's some element of the homology we're viewing as a path, and of course it doesn't, it's just some path. And so this is going to be the image of this segment under gamma. And then we can also, so we can think about this triangle, but translate it as the path 0 to infinity, and then, so that's going to be the image of this path, and then for this path, we can think of it as the image of gamma TS acting on 0 to gamma TS acting on infinity. And then finally for the last bit, this is going to be gamma TS TS acting on 0 to gamma TS TS acting on infinity. And the SL2Z is not, so here I should say T is this translation matrix, and S is going to be this sort of flipping matrix. And there's this relation that TS cubed is the identity. So we have these relations. The other thing that we need to know is that if we think about this going in the other direction, this is basically like saying S, right? This is going from infinity to 0. So what we'll have is that we'll have the sum of these three things equals 0, because we're going around this this triangle, and this triangle is contractible. And then we also have the following relation, that if you have gamma 0, gamma infinity plus gamma s 0 to gamma s infinity, that's 0, because that's just going up one of these and then coming right back down. So we've got these two relations that our symbols here are gonna, our modular symbols here are gonna satisfy. So I guess I'm gonna use modular symbol for both, meaning the things in the homology and the result of the pairing. So we've got this triangulation, and we've got these relations. So we have to also list the triangles we need to consider. So what triangles should we consider? And the answer is going to be that we need to consider the cosets of gamma naught n in SL2Z, because of course, as we've seen before, so using this notation here of parentheses, if we have, say, G gamma, for this is going to be G in gamma naught n, this is just equal to gamma in, sorry, not in x naught of n, but in the homology of x naught of n, right? Because where if we go from, this is just taking a point, say gamma 0, and mapping it to G gamma 0, which is equivalent to gamma 0. And so it's the same point in this quotient, x naught of n. So with what this means is that we need to look at coset reps. So coset representatives, gamma naught n gamma, so these are going to be, I don't know if people call this left coset or right coset, but cosets of this form, right? So it's going to be gamma is in gamma naught n quotienting SL2Z. Right, so a set of coset representatives that you can take for 11 you can consider 1, 0, 1, you consider the identity 1011, 1021, dot dot dot, 1010, so you have 11 of these, and then you also need to consider 0 minus 1, 1, 0. All right, so you can take these 12 coset representatives. In general, what is it? The index of gamma naught n in SL2Z is equal to n times the product p divides n of 1 plus 1 over p, right? So if it's prime, then it just, it's just 11 plus 1 here. So this is all you need to consider, and then there's also going to be some work to figure out when you have the same coset. So gamma naught n of, let's say, a1, b1, c1, d1 is equal to gamma naught n a2, b2, c2, d2. And then this is true if and only if, and this is a proposition in Cremona, so if and only if, so this is prop 2.2.1 of Cremona's book, and C1 D2 equals C2 D1 mod n. Of course, this is with these being elements of SL2Z, right? So when you do manipulations with modular symbols, and you get some coset representative that isn't one of the standard ones you've chosen, you can use this proposition to just figure out what you're working with. So there are also these maps, right, that A, B, C, D, you can think of this as the path, this corresponds to the path B over D, comma, A over C. So this is how you can break things up. And so you can really be thinking entirely of just the coset representatives, or the cosets, instead of paths for all of this business, and that makes you able to do the computations. So there's all this stuff about more being able to reproduce exactly the homology. Like there's a notion of boundary maps, etc. And that all sort of works quite nicely. So maybe I'll do an example in a future video of how you can use this to really get your hands on stuff. But the last really crucial bit is Hecke operators. So these act on modular symbols, and this is us exploiting the duality. So TP is going to be defined as follows. So if we've got some path alpha to beta, then we want to map that to the modular symbol P alpha, P beta. So here P is prime, and then plus some R mod P of alpha plus R over P, beta plus R over P. And if you define it this way, then you have the following, which is that if you look at this path as an element of the homology, and then take the pairing with the Hecke operator acting on the cusp form, this is equal to, if you used this definition to have the Hecke operator act on the modular symbol, and then you have this. So this is, this duality, this duality is what's going to allow us to compute stuff we want to know about our modular forms, in particular the Fourier coefficients, because we can use this triangulation up here to write out all the homology of x naught of n, so we know exactly what's going on the left here, and then we can write down what the action is of the Hecke operator on that homology, and we can find, say, its eigenvalues. And then once we found its eigenvalues, well, by this duality, that's giving us eigenvalues. So there'll be some sort of combination of these modular symbols here that is, I don't know, an eigensymbol of this TP, and then you're just manipulating this. That means that also that corresponds through this duality to an eigenform of TP. And so you can do that, and you can find its Hecke eigenvalues, and then you can find all the other Hecke eigenvalues, because again, these TPs commute, et cetera, and this is really how you're going to get at all this, these mysterious spaces of modular forms.